Hello, and welcome to the lecture on Unit 4. The homework that we have for this unit focuses on the differentiation of transcendental functions. My name is Dr. Paul Nussbaum. I'll be narrating the slideshow today. The overview of the reading really is Chapter 27. I'm going to try and cover points from each of the sections of Chapter 27 that you can see here. But not all the problems in the homework are going to be cleared just by looking at this lecture. I think all students should read the textbook before doing the homework if it's at all possible for you to do so. The homework mapping, as I've mentioned in previous units, it basically covers how to do the differentiation of transcendental functions. And it's really going to be important to form the foundation for the next class, Applied Calculus 2, that you're going to take in this series. Transcendental functions appear very frequently. It's just a fancy name for functions that can't really work with basic adding and subtracting and multiplying algebra, basically. So we have to do some special tricks to go ahead and manipulate them. And they're functions that you're already very familiar with. Sine and cosine, we see that in AC power, for example, very frequently. Also, a rotational motion of machines like motors and things like that. Logarithms, you've seen that over and over again. Natural decay of voltages or time constants for inductors and capacitors. You see that kind of stuff over and over again. So we need to learn how to do differentiation of these non-algebraic functions, and we call those transcendental functions. You can see in the next slide how we do that homework mapping. So some students will want to keep this sheet open as they do the homework. As you can see, it's over 40 questions, so trying to find where in the chapter the question relates to, sometimes it's easier to use a chart like this. This is the last topic that we're covering in this term. So Unit 4 is the last topic. I really don't want you to roll into Week 5 not having finished this, but just be aware that Week 5 is only for assessment. There is no additional homework, so I don't know if that is useful information to you. So the focus areas of the homework are kind of outlined a moment ago. And these are the areas I'm going to cover one by one in this presentation. So let's go through each section of Chapter 27. We start off with the derivatives of the sine and the cosine functions. Now, if you want the proof of this formula that's in the box there, you can certainly go to the beginning of Chapter 27. It's quite an elegant proof. It just shows how we can go ahead and find the limit as theta approaches 0 of sine theta divided by theta. Now you can see that both of those values, both sine theta and theta itself, approach the number 0 as theta approaches 0. So really you're asking us to solve 0 over 0. That's an impossible fraction. But using limits, we can see that it actually approaches the number 1. The fraction approaches the number 1. And you might want to review trigonometric identities. That's back in Chapter 20 of your textbook. I'm not saying that you have to memorize all of those. Also, I'm not saying you have to memorize all the derivatives of these transcendental functions. But you should know how to quickly look them up in your book. And then usually, like on a final exam, you have that kind of information available to you before you go ahead and take the exam. Just remember also the differentiation rules that we learned in the previous chapters, the power rule, the chain rule, etc. So let's, for example, take the derivative of the sine of 2x multiplied by cosine x squared. So here we can see that we would get the sine of 2x would be let's say call that u, and cosine of x squared, let's say we'll call that v. So we know from the chain rule that the derivative of u times v is u times the derivative of v plus v times the derivative of u. So here u is sine 2x and v is cosine x squared. So we use our tables to look up the derivatives of sine and cosine, and we find that the first row of the equation says sine of 2x times the derivative of cosine x squared, and we know that that's negative sine x squared times the derivative of what's inside the cosine, or the x squared. The derivative of x squared is 2x. Plus the cosine x squared, that's the v, times the derivative of u, and u is sine 2x. So the derivative of u is cosine 2x times the derivative of what's inside the sine 2x, which is 2x. So the derivative is 2. So basically a long equation is u dv v du kind of thing, and that gives us dx. So we combine like terms, and we see that the final answer is a negative 2x times sine 2x times sine x squared plus 2 cosine 2x cosine x squared. So it's a kind of long, but step by step, by knowing the derivatives of sine and cosine, and by remembering the rules of derivatives, power rule, chain rule, we can easily find the solution to this equation. The other trigonometric functions all have derivatives, and I've included a table here so you can see the derivatives of common trigonometric functions. So you can see here that the derivative of the tangent is the secant squared. The derivative of the secant is the secant multiplied by the tangent. The derivative of the cotangent is the cosecant squared. And the derivative of the cosecant is cosecant times cotangent. So you can see here that there's functions themselves, and you can see in the table the functions, and then in the formulas, those are the derivatives of those other trigonometric functions. Naturally, we want to find derivatives of inverse trigonometric functions. Sometimes on the calculator, the inverse of sine is written sine to the negative 1 power. Sometimes on other calculators, the inverse of sine is written as arc sine. So it just depends which calculator you're using. But if I take the derivative of the arc sine, it equals 1 over 1 minus u squared du dx. Remember that we're using u because we don't know what we're taking the inverse sine of. It could be x, in which case it would be simply 1 over the square root of 1 minus x squared. Or it could be a complex function of x, like x squared plus 3x plus 2. If you take the inverse sine of that, I have to let u equal that long function, and then I have to multiply the whole answer by du dx. So that's what this is showing in the formulas. You can also see that the inverse cosine is very similar. It's negative 1 over the square root of 1 minus u squared du dx. And the inverse of the tangent. That's a popular one. We use that to be the angle when we're doing polar coordinates, so that we use the inverse tangent or the arctangent quite a bit when we're finding polar coordinates when we have rectangular coordinates. So that shows us how that angle, that phase angle, changes over time if we know how the arctangent were to be calculated. So the derivative of the arctangent is 1 over 1 plus u squared du dx. So there are plenty of applications in electronics and mechatronics where we need to use trigonometric functions, and we need to find their derivatives or their rates of change. Let me give you an example of a physical system, a physical example that you might be familiar with. So we have some trees that we've cut down, and we've got logs. After you remove the bark, we've got logs that have a circular cross-section of 4 feet in diameter. And we are going to cut them in half lengthwise so that they're kind of these half cylinders, if you will. And I want to get the largest rectangular cross-section area that can I cut from those halves. What's the biggest in terms of beam cross-section, if I were to turn those half logs into beams, than those big rectangular planks of wood. So I want to cut off the two sides and the top and make it into a rectangular wooden beam, but I want to have the maximum cross-sectional area. So if I make them too tall and skinny, or if I make them too wide and low, it won't have the maximum cross-sectional area. So the formula here first asks you to kind of set that up. We already said that it's a circle, these logs, their cross-section, and they have a 4-foot diameter. So that tells us they've got a 2-foot radius, and you can see that here. But I've got a lot of choices as to that angle theta shown in the picture. Basically, that angle theta is going to decide how tall and narrow that cross-sectional plank is going to be. So if I go ahead and see that the beam is going to be twice as wide as whatever the number x is, and the height of the beam is going to be whatever the number y is in this kind of a right triangle here. And they're both related to the angle theta. So in the case of x, it's equal to 2 times the cosine of theta, and y is equal to 2 times the sine of theta, because theta being the angle and 2 being the 2 feet. So if I want the cross-sectional area of this wooden beam, A, we'll call it the capital letter A, that's going to be twice whatever x turns out to be, and that's because the bottom of this rectangle is twice as big as x. And the height of the rectangle is going to be y. So the formula for the area is 2x times y. So plugging in what I already knew x and y were equal to, I get 2 times twice the cosine of theta and twice the sine of theta. So pulling out the constants, I get 8 times cosine theta, sine theta. So now I want to use the trigonometric identity back from chapter 20. I don't know if you remember that. Cosine theta times sine theta is simply 1/2 sine 2 theta. So that's a trigonometric identity. You don't have to memorize it, but I mean, if you remember from algebra, there was a lot of little tricks you could use with trigonometric functions. So I'm going to replace that cosine theta sine theta with 1/2 sine of 2 theta, and 1/2 times 8 is a 4. So we know that the area is 4 times the sine of 2 theta. Now I take the derivative. The derivative of the area is the rate of change of the area with respect to theta. So the derivative of 4 times sine of 2 theta is equal to 4 times cosine of 2 theta times the derivative of 2 theta, which is 2. So the derivative of the area is 8 times cosine of 2 theta. So what I want is I want to set that first derivative equal to 0, because that'll tell me I've got a local maximum or a local minimum, or sometimes we call that a relative maximum or relative minimum. So I set 8 times cosine of 2 theta equal to 0, and I see that 2 theta has to equal pi over 2, so theta has to equal pi over 4. It's because I want to set the cosine of pi over 2, I want to set that equal to 0. So theta is pi over 4. So if I replace pi over 4 wherever I see theta, I know that my area is going to be a 4-foot square of that crosscut. The biggest area I can get cutting those beams is 4 foot. And if I want to go ahead and find the sine of 2 pi over 2, that's a 1. So that means the y is going to be equal to 2 feet, and the x is also going to be equal to the 2 feet. So that's pretty much how we go ahead and calculate the derivative and set it to 0 when I want to find a maximum. And we need to therefore know the derivatives of these trigonometric functions. Let's take a look at the derivative of logarithmic functions. You know, logarithms are used quite frequently in engineering. So let's take a look at how we calculate that. The logarithm base b in this case. So you know that if I push the LOG button on my calculator, that would mean base 10 logarithm, because that's the default value if no base is listed. If I push the ln button on my calculator, that would mean base e. So basically, okay, so fundamentally, the derivative of a logarithm, let's say a logarithm of some function of x, which we'll call u, that's going to be equal to 1 over u times the logarithm of e, all that multiplied by the derivative of whatever u was. So if u is simply the letter x, then the derivative of the logarithm of x is equal to 1 over x multiplied by the logarithm of e. So that's kind of a weird answer. Where did e come from? Well, we'll see here in a moment that if the base of the logarithm is e, we sometimes call that the natural logarithm, then the derivative is much, much simpler. So the derivative of the natural logarithm of u is simply 1 over u multiplied by the derivative of u. So that shows you that e is this special number that you can choose any kind of base of logarithm you want, but the only one that has a very simple derivative is the natural logarithm, only if it has a base of e. Let's go ahead and see some examples. Let's say we've got base 10 logarithm, which once again, if it's a base 10, I don't bother writing down the base. I just say log, and that's how it is on your calculator as well. So I want to find the derivative of y equals log 4x. So 4x is what we're going to set u to be. And we know that dy dx is 1 over 4x. Once again, 4x is the u, multiplied by the logarithm of e times the derivative of 4x, and that's a 4. So it's basically 1 over x times the logarithm of e. Once again, if you were to push logarithm of e, which is 2.71, etc., you'd get this value. The base 10 logarithm of e is 0.4343. Now let's say we take the natural logarithm. We write ln when we have the base of e. If we want to find the derivative, s equals the natural logarithm of 3t to the 4th, we would set u equal to 3t to the 4th, and the derivative would be 1 over 3t to the 4th times the derivative of that, 3t to the 4th, which is 12t to the cubed. Crossing out and canceling values, we get the answer is 4 over t. So that's pretty much how you take the derivative of logarithmic functions, whether they're natural logarithms or any other kind of logarithm. Exponential functions are when we're taking a constant and we're raising it to a power that's an entire function of x. So in this case, here you see that e raised to some function is equal to, the derivative of that is equal to e raised to that same function times the derivative of that function. That's the only one where it's simple. It's only when the base of the exponent e is the natural number, or Euler's number e. But in most cases, we're taking some arbitrary constant b, and we're raising it to the function, some function of x. So that's going to equal b to the u when I take its derivative, multiplied by the natural logarithm of b times the derivative. So you can see that always that natural logarithm comes sneaking back in there. Let's take, for example, and I don't want you to be confused, so I'm going to use two very specific examples. I've got a function of x, let's call it u, and I raise that to an exponent. That's very different from when I have a constant and I raise that to a function of x. Well, let's take a look at my function of x is, let's say, just 4x. So in the first case, I have y equals 4x raised to a constant power, 4x squared. In the second case, I've got y equals a constant raised to the 4x power, 2 raised to the 4x power. So their derivatives are going to be very different. Let's take the derivative of the first one. Y equals 4x raised to the second power. So we already know how to do that. I have to move the 2 down and then subtract 1 from the 2 exponent and then multiply the whole thing by the derivative of what's inside the parentheses. So I end up with 32x when I take the derivative of 4x squared. Now if I do the opposite and I've got the constant at the base and the power of x in the exponent, let's see how that works. Y equals 2 raised to the 4x power. So here, the derivative of y with respect to x is equal to 2 raised to the 4x powered multiplied by the natural logarithm of the base, natural logarithm of 2, multiplied by the derivative of that function. So you can see that 2 raised to the 4x is very different than 4x raised to the 2. When you take the derivative of the first one, you end up with 32x. And when you take the derivative of the second one, you end up with 4 times the natural logarithm of 2 multiplied by 2 to the 4x. Let's go ahead and take a look at a derivative of y equals the natural logarithm of the cosine of e raised to the 2x, kind of combining everything we've learned up till now into one formula. So we'll go ahead to the next slide and see how that's done. All right, so this is a more complicated one where we have to use everything we've learned up till now. So it's a good example to show how we would take the derivative of y equals the natural logarithm of the cosine of e raised to the 2x power. So it's kind of the chain rule there, where I'm constantly taking the derivative of the outside multiplied by the derivative of what's inside the parentheses. So we know that the derivative of the natural logarithm of some function u is equal to the 1 over u times the derivative of u. So what is u in that first case? It's cosine e to the 2x power. So the derivative of the natural logarithm of cosine e to the 2x is 1 over cosine e to the 2x times the derivative of cosine e to the 2x. We don't know what that is yet. So that's the first row of this equation. When you get to the second row, now we want to figure out what the derivative of the cosine e to the 2x is. Well, once again, using what we learned about the derivative of cosine, that's going to be equal to negative sine of u multiplied by the derivative of u. So let's write that down. Now I've got negative sine e to the 2x multiplied by whatever the derivative of e to the 2x is. And going to the third row, now we've got the negative sine e to the 2x in the numerator. We've got a cosine e to the 2x in the denominator. And now we're taking the derivative of e to some function of x. And we know that for the third row, e to the function of x, this derivative is equal to e to that same function times the derivative of that function. So e to the 2x, when I take the derivative, that's equal to e to the 2x times 2, which is the derivative of 2x. So basically, we're going to use one of those trigonometric identities, that sine of theta over cosine of theta, that's just equal to tangent of theta. I'm going to pull the constant out, and I got a negative 1 at the beginning, and then a 2 all the way at the end. I'm going to combine those and make that a negative 2. I'm going to put my e to the 2x first. So I've got negative 2 e to the 2x times the tangent of e to the 2x. So when you see a problem like this, don't be intimidated by it. Just step by step, we're using rules that we've learned all the way up till now. One rule that I wanted to point out is L'Hopital's rule. And that's a French fellow who figured out how we can go ahead and find functions that we normally couldn't find the limit of because they either blow up in one direction or another. He found a way that we can figure out those limits. So we didn't use L'Hopital's rule at the beginning of the chapter when we derived found the derivatives of those trigonometric and logarithm functions, but we could have used L'Hopital's rule to do that. And section 7 of chapter 27 kind of goes through some of those proofs. But basically what happens is we've got some function that we can't evaluate at some point A because it turns into some fraction that's either a 0 or divided by 0 or infinity divided by infinity. It's just really tough to figure out. So if that function is a fraction, like u of x divided by v of x, we can use L'Hopital's rule to figure out what the limit as x approaches a of that function u of x divided by v of x. And it turns out the limit as u of x divided by v of x approaches a, or x approaches a, is equal to the limit of the first derivative of u of x divided by the first derivative of v of x, also as x approaches a. So it's an interesting rule that says if I've got two functions, one divided by the other, that fraction is equal to the derivative of those two functions, one divided by the other, or the slopes, or the rate of change, or however you want to call derivatives. So I can also repeat that more than once. So if it doesn't work with the first derivative, I can say, well, let me use the second derivative, or the third derivative, the fourth derivative, and keep going until I get a reasonable function that isn't 0 divided by 0 or infinity divided by infinity. Let's take a look at an example real quick. I've got some function, x squared plus 1 divided by 2x squared plus 3, and I want to know what does that function tend to as we go into infinity. Well, I can't really just plug in infinity because I'll have infinity divided by infinity. That's not really useful. So I go ahead and I realize with L'Hopital's rule, the ratio of x squared plus 1 divided by 2x squared plus 3, that's going to be the same as the ratio of their derivatives. Take the derivative of x squared plus 1 and the derivative of 2x squared plus 3. So now I want to find the limit as x approaches infinity of 2x over 4x. Well, that still blows up to infinity. So I have to take the second derivative. I take the second derivative of that numerator, and that's what's the derivative of 2x? That's a 2. What's the derivative of 4x? That's a 4. So 2 over 4 is equal to a half. So I find out that the limit as x approaches infinity of this crazy function is actually tending towards the value 1/2. So it lets us solve some problems, like example, some electronic component that was settling towards some value as time equals infinity. You know, we don't know what that value is. We can go ahead and use L'Hopital's rule by repeatedly taking derivatives and figure out that fraction. So let's take a look at an application of everything we've learned up till now. We've learned about trigonometric functions, how to take their derivatives, logarithmic functions and take their derivatives. We learned about L'Hopital's rule. And this last part of chapter 27 just lets you try a whole bunch of different engineering problems where you end up using these kinds of things. So first let's take a look at a resistor that's using up energy in joules, and after t seconds, the amount of energy dissipated, or how hot it is equal to E is equal to the natural logarithm of t plus 1 minus 0.25 t, minus a quarter of t. So at what time would the energy dissipated be the greatest? In other words, what time is this resistor going to be the hottest? We often need to know that because maybe we've designed a circuit with certain cooling aspects. So we need to know how hot is the particular resistor going to get when it's at its hottest point. So if I have some curve, I don't know what the shape of the curve is, so we can definitely draw that, but it's not necessary in this case. I know that it has some curvy shape, and I'm going to want to find where the first derivative equals 0, because I know that's going to be either a local maximum or a local minimum, or a relative maximum, relative minimum. So I'm going to let u equal t plus 1. And you'll recall that the derivative of the natural logarithm of u is equal to 1 over u times the derivative of u. So the derivative of the natural logarithm of t plus 1 is equal to 1 over t plus 1 times 1, because the derivative of t plus 1 is 1. E also has that value minus 0.25t. So in total, the derivative of E is 1 over t plus 1 minus 0.25. So solving, I'm looking for a value where that first derivative equals 0. So I set 0 equal to 1 over t plus 1 minus 0.25. Then I'll add 0.25 to both sides, giving me a positive 0.25 equals 1 over t plus 1. Then I'll take the reciprocal of both sides, and I'll end up with 4 equals t plus 1. So the answer is t equals 3 seconds. This resistor is going to be dissipating the most energy at 3 seconds after the whole process begins. So that's an application where we had to know the derivative of the natural logarithm. That's very common. It's like the decay of a capacitor charge or an inductor current decaying over time. So natural logarithm comes in quite frequently in electronics engineering technology. So after you finish the homework for chapter 27, you're going to have obviously an assessment. That'll be available to you week 5. It's a quiz that's covering all of unit 4. And all of the 18 questions in the quiz obviously are going to come from this chapter. It's an important chapter, and that's why we dedicated an entire unit to it. Also, the final exam at the end of the term, which is also in week 5, is going to have about a dozen questions on this chapter, and they're going to be focused on finding the derivative of different trigonometric functions and then using those derivatives, finding the derivative of different logarithm or exponent functions and then using those derivatives, using a calculator, so being able to push the buttons on your calculator properly, sketching a curve, local minimum, local maximum, as well as concave up and concave down, the first and second derivatives, finding the rates of change. And then there will be at least one question where you have to use L'Hopital's rule on the final exam. So make sure you know how to quickly look up those derivatives of transcendental functions, the trigonometric and the logarithm functions, as well as how to look up things you might need to solve those equations. The study sheets focus on the definition of 2 key terms that you really need to understand to be able to understand Chapter 27. The first is what is a transcendental function, and the second is what is L'Hopital's rule. So the other terms used in the chapter are really reminders of past math and engineering. So if you're kind of rusty on that, feel free to look back to Chapter 20, all those trigonometric identities. Once again, you don't have to memorize those, but you do need to know how to look them up. Listen, thank you so much for listening to our lecture today. All of the pictures, diagrams, and formulas come from your textbook, Basic Technical Mathematics with Calculus, 10th edition from Alan Washington and Pearson. So all of them come from that chapter, so if you encounter them, you want to go look up more details, please go back to that chapter. Once again, thank you for listening.